Okay, so now we've hopefully had a quick overview or a brief refresher on what vectors and one-forms are. Let's take this up a notch and start to look at a tensor. So I'm going to explore the metric tensor in a lot more detail now. If you remember, I sort of briefly introduced this object, which we refer to as the line element, which essentially gives the infinitesimal squared distance, or the squared separation between any two points in our geometry, and we calculate it using this new object which I introduced, which we give the name g. So this g new object is representing the components of our tensor, and then we have our tensor basis. So the expression which I've written here essentially just defines a 0-2 tensor. We can just take this as the definition of, or rather the expansion of, a 0-2 tensor. These are just the components, and then this is just the tensor basis. So if you'll recall, this g is going to be a 0-2 tensor. Essentially it has two lots of the one-form basis. We string them together using the tensor product symbol. And now if you're not too familiar with how these tensors or multilinear maps function, I would encourage you to go and look at one of my other videos where I explored this in much more detail. But now just to kind of give you the really quick summary of how this object works, or how we should view it as an object. Essentially, well, it's going to be a map. It's what's known as a multilinear map. And now how we should view this tensor product symbol is that it essentially is what we use to kind of string together and form higher order tensors out of just simply vectors and one-forms. So I could write an arbitrary PQ tensor. It's just going to be some object, I'll call it T. It's going to have some amount of upper indices up to this number P, and then it's going to have some amount of lower indices up to this number Q, and then we simply just have to introduce, well, these are just the components. We now have to kind of give the actual tensorial part of this object, which is going to be the vector and one-form bases. So what this tensor is going to come with is essentially going to be now p copies of a vector basis. So this is going to be u1 and then p lots of a tensor product up to mu p. So these are kind of the vector parts of the tensor, and then we just have, run out of space a bit there, but essentially the one-form parts of the tensor, they're all strung together using this tensor product symbol. And now this is one way of expressing the tensor. It kind of is a bit unclear as to really what's happening. A notation which I much prefer is this kind of angled bracket notation, which really kind of emphasizes that this object dx mu is something which is waiting for an input. So I'll just rewrite this. We have our components, and then we introduce our basis, and now we express the basis using our kind of angled bracket notation. And so this first object which I've written here is just simply this basis vector, but I'm making it explicit that this kind of whole object, this is a single object which I've written in the red brackets. It's waiting for some kind of input into this slot here, which is going to be one of our one-form bases. And then we have our tensor products, all the vector ones, and then we eventually reach the one-form part, and then we just simply start writing one-form maps instead of the vector maps. And now this is just, again, waiting for us to insert some kind of vector in there. So this is essentially now what the tensor looks like when fully written out as a essentially just a kind of string of these maps. And we can see that all the tensor really is just some, well, yeah, it's a big long combination of these vector and one form maps that we're kind of chaining together using this tensor product symbol, which all it really means is just essentially telling you, okay, we need to treat each of these vector bases as their own kind of independent linear slot that this tensor can, or that can be receive inputs, and then this object is going to be linear, so we could have had A plus B in this slot here, and then we can just simply split the whole map as being A tensor product blah 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 plus B tensor product blah blah blah. That's essentially just a statement that this, introducing this symbol, we respect the linearity of each of these individual maps. Okay, so that's what the tensor looks like. It's essentially just waiting to eat any number specified by the rank of the tensor, any number of vectors and one forms. So we can see here our metric tensor, being a 0,2 tensor, is essentially now waiting to eat two vectors, and we insert each vector into one of these one forms. So let's actually perform this calculation now and see what actually happens when we feed vectors into the metric. So I'll just begin by essentially just rewriting this expression using the angled brackets. So we're going to have, so all I've done is just rewritten the definition of the metric as a tensor using our angled brackets. And now we can sometimes just kind of forget about the tensor product symbol and leave it implicit. I'm just going to leave it there for now for completeness. And now what this thing is going to do, as is clear from this notation, it's waiting to have these two slots filled, and it's going to be waiting to have some kind of vector put into each of these slots. Okay, so let's just start by just simply doing a quick calculation to show how this is going to happen. If I introduce now a vector, which I'm going to call v, so it's going to be expressed in terms of its components and then the coordinate basis. Hopefully you're familiar, or I introduced how this is defined in the previous videos. But now let's plug this vector into our metric and see what happens. So I've already used the index mu just to be consistent. I'll give it a new index, let's say sigma. And now let's see what happens when we feed now one vector, just a single vector, into this first slot here. So I'll just, without writing out the full expression every single time, what we're essentially just going to need to do is plug this v into here and calculate the result of this angled bracket here. So I'll just write it here. Now let's sub in the vector expression fully expanded. And now what we need to remember is that these v sigmas, these components, they're just essentially real numbers. So they don't have anything to affect either of these one form and vector parts. We can just pull them out of this angled bracket, and so they just become a scalar multiple outside the bracket, and we're just left with that's a sigma there. So now if you remember back to our video where we introduced vectors in one forms, we've said that this expression here is essentially how we do all of our calculations, is we boil them down to an expression that looks like this, and then we just use our rule or our law that we kind of stated but then saw where it comes from pictorially, that essentially when we contract the one form basis with the coordinate basis, we're just left with this Kronecker delta here. And so now you'll see this whole object just being this Kronecker delta. When we contract the sigma index on these components, it's just going to reduce this sigma index to the mu. And so this whole expression is just going to be v mu. So okay, that's what happens when you evaluate this single bracket with a single vector. Now let's just remember we were not writing the whole expression, but let's just write it in full now. So after we've put one vector into this slot, we see that that kind of single bracket just kind of extracts our components of the vector, like so. And so this whole expression is now going to leave us with an object that looks like this. So now we should realise further, well, first of all, we can immediately sum this new pair of contracted indices, and we could say, okay, well, we've got a fully summed index that's just going to disappear, and we're only going to be interested in this new index. So I could reasonably call this whole object, remember it's just a set of numbers multiplying some other set of components. I can just call this a completely new set of components. Let's call them v hat. And now to remember, respecting the indices, the only free index left is this new. So our metric components are contracted with the vector components that we found by feeding our vector into one of these one forms. And we're just left with now what looks like not a set of vector components, but now a set of one form components because they have a lower index. More on that very shortly. And now the only kind of vector or tensorial part of this expression which is left is this just single dx new object, which is just going to be a 0, 1 tensor, or just a single one form. So all that we're left with is essentially the following expression, which hopefully you should now realise is essentially just a single one form. All that we have is a set of one form components and then a single one form basis. So we should realise now that what's happened, well, let's just remember what we did. We started with the metric and we fed it now a single vector, just this one vector v. When we expand out and perform this map using our Kronecker delta rule, we're just kind of given the components of that vector. And then what we saw happens here is that when we kind of multiply or contract this set of components with this g mu new object, it kind of effectively just gets turned into a set of components with a lower index. This is sometimes known as index lowering, I'll say more shortly. But all that happens now is that we're left with essentially an object which looks like, or it is, a one form. So how we should now really interpret this is that what the metric is doing is it's taking a single vector and effectively turning that vector into a one form. So I'll just say a little bit more about this now.